Professor Palffy-Muhoray and also Mr.
Yeah, so I'd like to finish up on topics that I was talking about, and but before I start, I wanted to get back to the Heidinger's brush problem, because some people ask me questions about this. So the idea is that in our foeva we are polarization sensitive, and you can see this if you look at a surface from where you have polarized light coming. And so if you look through this little polarizer at some fairly uniform surface, then you should see polarized light coming through the polarizer to your eye, and you should see Heidinger's brushes. And so but it takes a while to see it, and what you should look for then is this horizontal figure 8 with yellow lobes and a vertical figure 8 with blue lobes. And just to give you a sense of the size of it, for me, it's more or less as wide as my thumb when I stretch out my arm. And so if I look at the surface, then I can see a faint, this faint Heidinger's brush pattern. And so it takes a while, and if you play with it for a while, then you should be able to see. A thing that worked really well for my students at home is we have a diffuser over the fluorescent lights, which is flat. And if you look at that through a polarizer, then you can see it really pretty clearly. So that's a good kind of surface to play with. Okay, now there was one topic that I wanted to cover in my first lecture, but didn't have time. So I'd like to say a few words about that. And it is this idea of liquid crystals being so responsive, and the reason for that, at least from one perspective, is Goldstone's theorem. And Goldstone said that if we have broken continuous symmetry, we will have necessarily symmetry mandated low energy excitations, which make the materials really responsive. And so the question is, how exactly to understand this statement, and specifically how it is the broken continuous symmetry that leads to this. So let me give you my take on this after considerable meditation. So in this naive picture, at high temperatures we have rod-like particles oriented every which way, and then if we lower the temperature, then below a critical temperature, they will orient, so on the average they point in some direction, which we call the director. So the point is that initially, imagine you're out in space, no preferred directions, the director could end up pointing anywhere. So essentially, once you go through the transition, you're breaking the symmetry of this undifferentiated manifold, which is the surface of a sphere, if you like. And the point, I think, of this broken continuous symmetry is that the direction is arbitrary, and that just means that there is nothing there to define a direction. So there's no field present, because if there was a field present there that would define a direction, then the argument would no longer hold. And the argument then simply is that because there is nothing else, the only interaction you have is between neighboring particles, and then it follows that the energy associated with changing the orientation can only depend on the gradient, because you're only considering your neighbors. There's no other field to couple to. So I think that's the essence of the argument, that the broken continuous symmetry means that the only thing that that your particle can interact with is the neighbors, And therefore, the only thing that can matter is how rapidly you're changing orientation, in this case, relative to your neighbors. And so the energy then of long wavelength excitations is vanishingly small. And well, I mean, so that's what we see in the Frank energy, that essentially the energy of deformation goes as a gradient squared. So, so I think that's at the heart of it. And this then holds for every other system where you have this broken continuous symmetry, where only the order, whether that's orientation or position, in the case of phonons, this argument has to hold. And this has sort of interesting consequences, because if the deformation energy, suppose you have a sinusoidal deformation field, then the energy will go as the amplitude squared, and if you have a wave vector q, then it will go as q squared, and of course we have some elastic coefficient, and the equipartition theorem holds in Fourier space as well, and so the energy of a mode with amplitude, let's say AQ, is going to go as KT, okay, ignoring scaling by volume and things. And so if you want to know how big the mean squared fluctuation amplitude is, then you need to integrate over Q space, and the amplitude squared of each mode is just KT over elastic constant times Q squared. And then you have to integrate, and in 1D, the elemental volume is just dq, and if you integrate this, then you get 1 over q, and basically we go from q being 0 for infinitely large systems to some q max. Okay, there's some smallest wavelength of deformation. And so here we have a divergence, because we end up after integration with 1 over q, which blows up at the bottom, and this is the Peierls instability. And so this is in 1D, and in 2D we have q dq, and we get a logarithmic instability, and that's the Mermin-Wagner, Hohenberg, who did it differently. And so this is a logarithmic divergence, so this is much weaker. And then finally, in 3D, everything is good, because we have q squared dq, and there's no divergence anymore. So this sort of follows from the original theorem. But I think it's an interesting notion, and I just want to mention this. So it's this broken continuous symmetry argument, I think, that ultimately makes soft materials responsive. Okay, so I want to get back to cholesteric structure now, and we talked about chirality and the association with pseudo scalars. And so if we write the Frank free energy, then we have 1/2 K1 del dot n squared plus 1/2 K2, and now we have n dot del cross n, and this quantity is a pseudo-scalar, and if we have another pseudo-scalar in the problem, which could come from the structure of an aromatic molecule or from the structure of some chiral dopant that you put into the system, then you could add or subtract that pseudo-scalar here, and then we have this interesting new term, and then we have the usual K3, which is n cross del cross n squared. And so then you can ask how to minimize this free energy, and it turns out that the minimizer in the appropriate coordinate system just ends up being cos QZ sine QZ 0. So this is sort of formally how the helical cholesteric structure arises that I mentioned before. And then because of the periodicity and Floquet's theorem, we get the band structure and so on. And of course, if we have an electric field, then there's another term in the free energy, which is this minus 1/2 epsilon naught epsilon parallel minus epsilon perp E dot n squared. Okay, so this is the regular cholesteric structure. And it's interesting, of course, to speculate as to exactly what this quantity is, given that you have either chirality in your molecule or some chiral dopant that you are adding. Right. So then we showed that this helical cholesteric structure gives rise to a band gap, and actually we only talked about the lowest band gap, but it has lots of potential uses, and so we'd like to be able to tune the band gap to be able to shift it around. And so the question then is how to do that, how to tune the structure. Yeah, but before we go to the tuning part, I just want to say a few more words about actually making this structure. So typically, one would add chiral dopant, so it makes a molecule which is really chiral and is soluble in the nematic that you start with, and then you develop a cholesteric structure, and you want to be able to measure the pitch, and one way of doing it is to make a wedge, a Grandjean-Kano wedge. And so basically what happens is at a certain thickness, you have a certain number of turns, certain number of half pitches, and then as the thing gets thicker, you have to increase the number of half pitches, and in between these regions, there have to be some defects. And so because, yeah, on the surfaces, the nematic director is continuous, but in between, something has to happen. And Oleg and Ivan Smolyuk did some really beautiful experiments studying what happens between these regions where the thickness is commensurate with the pitch, and one sees really interesting structures, both dislocations and disclinations, that have been really beautifully studied and analyzed in this paper. So if you're interested at all in this, I recommend this paper from 2002, because it's really a beautiful piece of work. So typically, one would make a mixture and put it into some sort of Kano wedge, and then one can determine the pitch, and then one can add more or less chiral dopant to get to where one wants to go. And so I don't know if you can see, this is a cylindrical Kano wedge, so it's just a spherical lens that you put on a flat substrate, and you have the liquid crystal between a flat substrate. And here you get circular defects, and by changing the concentration, one can change the pitch, and by plotting the pitch versus inverse concentration, one comes up with this helical twisting power. So here, this is the concentration in weight percent, and this is the pitch. And so this is a measure of goodness of the chiral dopant, and so you may see this helical twisting power. So one can adjust the pitch of the structure appropriately and come up with whatever band gap configuration that one wants. And then we come to the question of tunability, because we'd like to be able to shift the reflection band at will. And I mentioned that there are different strategies. One can use mechanical deformation, and one can change the temperature. But the really intriguing question is, can we use electric field to change the director? Now, if you just look at this, it's not really obvious what the electric field would do to a given configuration in minimizing the energy. And I'll come back to that. So I mentioned that, so this is a cholesteric rubber made by Heino-Finkelman, and the pitch, so the helix axis is perpendicular to the plane of the little rubber sheet, and when you stretch it, due to volume conservation, the thickness decreases, and therefore the pitch also decreases, and so that shifts the band gap, and then you can see the laser lines that we talked about before shifting correspondingly. And this is just a sample we were playing with. So if one changes the temperature, one sees a modification of the reflection band, and it's pretty sizable, but it's not really completely, well, it's not clear even what the dominant effect is, because everything changes as a function of temperature. The order parameter changes, therefore the elastic constants change, the polarizabilities change, so everything kind of changes. And one certainly gets a big effect, but you see that the bandwidth gets narrower, the amplitude gets smaller. And as I said, it's not a very effective way of controlling the band gap, because it's hard to keep the temperature constant, especially if you imagine some sort of application. So it would be better to go on to a different strategy and to apply an electric field. And this shows what happens if you just apply an electric field to a helical cholesteric sample. So again, the alignment is planar, and the director rotates, and we apply a field in the perpendicular direction, and nothing much happens, as you can see. Now, in different samples, you see slightly different behavior. There's some change in this case, there's some change of the band edge on the long wavelength side, but mainly what you see is the amplitude changing, nothing else. So this is not very satisfactory at all. And you can then ask of what is it that one would expect if you apply an electric field to a helical cholesteric structure. So let's imagine that we have a cell. So this is a side view, and we have some sort of helical structure inside. Okay, let's imagine that. And then I apply an electric field here. Okay, what do we expect to happen? And as you can see, to first order nothing, because essentially the electric field polarizes the molecules, and that's about all that happens. There's no torque on the director in this case. There will be some effect that the electric field will change the order. So in fact, it'll make the system somewhat biaxial, but other than that, not a great deal will happen. It will quench fluctuations perhaps. So the effects are small, and certainly, as you can see, experimentally, not very useful. If you ask what the ground state of this configuration is in an electric field, you'll see that what would work best is if this structure could rotate 90 degrees, because then at least half of the molecules would be aligned with the electric field. Right? So, and in fact, that's what happens, as I'll show a little later on. Now, there was an idea that came from Bob Meyer and Pierre-Gilles Dejean, which basically said the following, that suppose that we have an electric field which is so strong that it unwinds the cholesteric, and all the molecules are aligned like this. But this system is a cholesteric. It's an unwound chiral cholesteric. And so if you were to then reduce the electric field, then you would expect that somehow this term would become important, and you would see some sort of helical structure developing. So the expectation was that if one did this, then as you reduce the field, this would eventually transform into a structure where there would be tilt, and these molecules would presumably somehow be sitting on some sort of conical structure and wind as you go through the cell. But experimentally, this was not found. So this was not observed. And it turns out that the reason it wasn't observed is because this K3 term prevented this state from being realized. So, so this was due to the influence of K3. And then at some point it was realized that K3 could be reduced fairly effectively by making bendable molecules. So, bendable. So K3 basically is the cost of changing the director if you move in the direction of the director. And if you could make molecules that would bend easily, presumably that would reduce K3. And so this takes us to the dimer, and this is a molecule that basically consists of the typical nematic molecule 7CB. So this is just a typical cyanobiphenyl here. And then there's a 7 carbon long alkyl chain here, but there is its twin over here. And so this is mesogenic, and because of this flexible alkyl chain in the middle, it bends really easily. And so adding these dimers to a typical nematics enables the realization of this heliconical structure. And so the next key paper really again goes back to Oleg's group, who did this really beautiful work analyzing the electro-optic response of nematics with oblique helicoidal director. So this is really, I think, an outstanding paper. And this basically shows what happens in these mixtures with the small K3 when you apply and reduce a large electric field. So this is sort of side view of a cell, and this shows a completely unwound, this is a high field, so it's almost 3 volts per micron. So this is an unwound pneumatic, as indicated here. And as the voltage is reduced, then indeed it goes into this heliconical structure where you can see the periodicity along the electric field. And then as the field is further reduced, the structure indeed goes over into the conformation I talked about, where the helical axis just rotates 90 degrees relative to the field. So, and then there are equations that one can get by essentially looking at the Frank energy and asking which conformation minimizes the Frank energy, and I just want to put these on the board. So there's a critical field so this is in going from the unwound pneumatic to the cholesteric, and this critical field is 2 pi over P naught, where P naught is the pitch in the original cholesteric divided by times K2 divided by epsilon naught delta epsilon times K3. So this is the field where the unwound pneumatic becomes chiral again, and there's some really interesting things that come out. Is that the pitch is 2 pi, so the pitch in the heliconical structure is 2 pi divided by E by the electric field times K3 over epsilon naught delta epsilon. So interestingly, as you increase the field, so as you're closer to the unwound state, the pitch gets shorter, which is a little counterintuitive, but that's how it works. And the tilt angle and I'll write it in this form with kappa, which is the ratio of the elastic constants times E and C divided by E minus 1. So kappa is K3 over K2, and usually this is greater than 1, but for the heliconical structure to be realized, kappa must be less than 1. So the trick is to make K3 as small as possible. And so what you see is that at high fields, then the cone angle goes to 0. And these two graphs here show that the pitch indeed decreases with increasing electric field, and the cone angle decreases with increasing electric field according to these results. So I think this is really fundamental work. And finally, there's another critical field where the director rotates so the helix axis rotates so as to become perpendicular to the applied electric field. And so this is just well, it doesn't matter what the subscript is here. So this is just the original critical field times kappa 2 plus 2 1 minus kappa divided by 1 plus kappa. So basically these are the two fields in between which one can see this heliconical structure. So this is really a great step forward, because it enables then to make these materials tunable, essentially by virtue of this result, where the field changes the pitch, and as we know, the pitch essentially determines where the band gap is. So now Miha has done some very nice work with his co-workers, modeling the properties of these structures, essentially looking to see where the band gap is at different tilt angles and different pitches. So this is a very nice paper. And then finally, I just want to mention work we did together with Oleg's group, using this tunable aspect of heliconical structures to do lasing. And so this is a schematic of what happens. So as you increase the field, the pitch gets shorter, and then one gets lasing typically at the band edge, as I indicated below, and by applying a voltage, one can then shift the laser line in a very beautiful, controllable way, which is both fast and accurate. And so there are two separate curves here, because the dye fluorescence spectrum is limited, and so one dye works well in this regime, and a different one works well in this regime. And one, of course, can use a mixture of dyes to extend this range. And so this is just a picture, again, showing really beautiful, very narrow laser lines. And you can see that they're really tunable all the way from 540 up to well past 700 nanometers. So, so I think in conclusion, this heliconical structure really opens the door to all manner of applications, because of this precise and relatively straightforward control of the photonic band gap. And there's one open question which involves the pressure dependence of the structure and its optical response, and we don't know anything about that. But it's even a bigger question, because we simply don't know the pressure dependence of pneumatics or other liquid crystals, because very little experimental evidence on this. And theoretically, there is no viable equation of state. And so I really see this as an outstanding problem in the field. And the problem, as I try to indicate, I mean, the crux of the problem is the question of free volume when you pack anisotropic particles. So it's as I said, it's intractable even for hard spheres, and it seems even more intractable for non-spherical objects. But I think that that's an area where really work needs to be done, and that's probably a challenging problem for mathematicians as well. So I think that's an area that really requires attention, and I think that will lead to big steps forward in being able to design and use these materials. Because as I said before, in principle, we know already everything we need to know. We know the excluded volume issue, we know how to quantify that. We know the strength of the London dispersion, sort of remarkably from the uncertainty principle. We know how big the spontaneous polarization is. So we can compute pretty much explicitly the strength of the interaction between these particles. So we have the hardcore repulsion well under control. We have the attractive interaction well under control. So the question then is how to use these parameters to go all the way to an equation of state. And the real issue, I think, in developing sort of a continuum model in density functional form is getting a reasonable handle on what the free volume is, which is just really the entropy associated with steric interactions. Well, that's pretty much the end of my story, but I want to leave you with a little sort of anecdote that I came across recently, given that I mentioned entropy just now. And I like jokes, as you know. And I came across, by complete accident, an article that talked about jokes, humor, and entropy. And I thought, what connection could there possibly be between humor and entropy? But interestingly, this paper mentioned that Claude Shannon, who is the father of information theory, defined something called a surprisal. And a surprisal is just the amount of surprise you have when you encounter some data or some observation. And a surprisal is just minus the natural logarithm of p. So you have some event with probability p, and if you see that, this is how surprised you are, according to Shannon. And if you think about it, this is pretty good, right? If the probability of something happening is 1, well, I'm not too surprised, right? But if the probability gets to be really small, yeah, you're surprised big time, right? So that's surprisal. And then entropy, of course, is just how surprised you are on the average, right? So just pi log pi. So I don't know. I thought this was pretty interesting. I had never thought of entropy in this way. And it's true that in humor, I think, you know, it does play a role, because typically you hear a joke and at the punchline there's some surprising thing and you think, my God, I don't understand this. And then suddenly you understand it and you're relieved, haha. But I think that it is the unexpectedness somehow of events that makes humor what it is. Anyway, I thought this was an interesting story. All right, thank you very much for your attention.
Okay, one last round of questions.
So when you
Oh, yes. Hold on. Yes, go ahead.
So in the situation when you apply electric field along the helix, so in that particular state, what do we call liquid crystal? Is this pneumatic or cholesteric? When we have unwound the helix.
Well, yeah, there's some imprecision in the language. And I would call it an unwound cholesteric. That's what I would call it. I mean, it's clearly a chiral material, and so it's not completely clear whether cholesteric refers to the texture or to the substance. You know, so I would call it an unwound cholesteric, but strictly speaking, it's just a kind of a nematic, really.
But it is
It has a symmetry. It has a symmetry of a pneumatic. Oleg, what is your opinion on this?
call it anyway, but when you need to put the subscript, like the transition from unwound to not unwound cholesteric, then pneumatic is much easier because you just put n as a subscript. So it's a taste of shortness in notations.
you mentioned this open question of pressure dependence. So could you perhaps say a bit more on that?
Well, you know, I mean, we have the equation of state for fluid, and basically it's just P equals something. And I mean, presumably there is such a thing for pneumatics as well. And indeed, there are models out there now that have, you know, essentially equations of state that relate pressure to volume, temperature, and orientational orders. And it is this coupling that really makes the question interesting of, I mean, you know, we know that if we want to reduce the volume of hard rods, we have to increase the orientational order. So we're kind of fighting against orientational entropy as well as positional entropy. And now there have been experiments quite a long time ago by an Indian group from Bangalore, and but interest really had more to do with the effect of pressure on phase transition than on just simply how the materials behave, how the order parameter, for example, changes. So we're trying to get to the point where we can do some experiments and talking to people who can do experiments to measure essentially the pressure dependence of by the fringes, for example, or dielectric constant, I think.
Peter, why are you interested in pressure dependence in connection with lasing? I mean, it seems a beautiful enough effect by itself, but why do you want to fold pressure into that?
Why to gild the lily? Well, just simply, it's an interesting question as to how pressure will change the order parameter and consequently how it will change the band gap and the laser line. I mean, one example is that, you know, these lasers are actually pretty good sensors of the state of the system. So we made, for example, an optic fiber that had a hollow bit, and we put some cholesteric in there. And it's a wonderful temperature sensor. You can put it at the end of a 10-kilometer optical fiber. You shoot a pulse down there, and it comes back and tells you what the temperature is. So it could be used for sensor applications, but I think it just, I mean, the pressure dependence is not coming from the band gap aspect of the material. It's generally
Be a remote pressure sensor. If you understood how the laser changes with pressure, you could remotely sense pressure variation.
Yeah. So just like temperature, you could use it as a sensor. That would be one application. But I just feel I feel that we've neglected this somehow. Every other simple thing has an equation of state with a few constants, and away you go. And we simply don't have anything reliable. And the problem is basically, I think, that these are dense materials, and the models that we have simply don't get anywhere near those densities. You know, Onsager himself estimated that his theory is valid up to 0.2 something volume fraction. But interestingly, it seems to work beyond that, but just the same, you know, if you think about how dense liquid crystals are in terms of volume fraction, they are really pretty dense. And now, people who look at hard sphere models, they do cluster expansions and they work like hell to get a little better, but it's all in the low density regime. I think we don't need such accuracy, but we need a reasonable approximate description of what happens up in the high density regime.
Could this pressure, temperature, say, relation be obtained from some of the continuum models that we have? For example, in Landau-Dijon's, we have temperature and order parameters. Would that be good enough to estimate pressures? The only thing that we don't have is somehow any condition or any expression for compressibility.
Well,
so if we could relate that.
I mean, as soon as you have an expression for the free energy, in principle, you have an equation of state, because you just take your derivatives and away you go. But the problem is that the density dependence of the free energy is either non-existent or it's very, very poor. So that's the issue of how to get an expression for the free volume as a function of density. And it's so simple because you know what it is at very low densities, you know what it is when the thing is completely crystallized, but you don't know how this curve goes from the two endpoints. And it's sort of seductively simple, and when you try to get at it, it gets really complicated.
Any more questions? Well, otherwise, let's thank Peter and all the speakers of the week. It's been fun.